Okay. So this is the thing in short that is called the BIB tool, which stands for Broad Ion Beam Milling. So the particular machine here is a Hitachi version called IM4000. So what this machine do is that it makes cross sections of your sample. The alternative technique to this is a thing called the focused ion beam technique, which is the same machine inside the SM. But these are complementary tools because the focused ion beam can make very narrow cuts. So the cuts widths are like in hundreds of micron perhaps in the SCM. But on the contrary, you get this very nice, what shall I say, selectability. You can, by the SM's magnification, choose here I want my cut. Right? This machine doesn't have that because we work outside the microscope. But in return, we can make much wider cuts, hence the name broad ion beam. So the cut widths here are up to 4 millimeters, which is a lot in this business. And that makes it, what shall I say, a completely necessary tool for when we're working with paper or fiber-based material, because fibers are like hundreds of microns. So you need this very full width. The machine, it's like a bench tool like this. The sample will go in here. The thing that you see here is the jig that the whole material, the sample will be mounted in. And we will talk more a little bit later on this, but what we see here is the mask. So the technique works like to the left here, there will come in an argon plasma beam, will go straight above the mask here and just erase everything that points up above the mask. Hence, that's how it works. So these mask pieces are made of titanium. They are consumables, so one can rotate this along, so one can flip up each of the 4 edges and you can move them around. So, but after a while, this wears down, so then you need to replace them with a new one. This machine also has an extra feature, so instead of cross-section milling, it can also do flat polishing. So if you have something that is polished, it can you can sort of make that the last final fine-tuned polishing step to make it super crisp, as I say. But we don't use so much of that technique. So I'm going to show you how to mount the sample in this machine. We will look on the end result, how it looks like when it comes out from the machine, and how to make the sample preparation for the SCM. So we go to the other lab. So now we are here. Depending on how many samples you're having, it can be beneficial to use one of the bigger stub pieces. Today I have 4 samples. So if you have a small stub piece, you usually manage to fit 2 cross sections on it. So hence I use the big one. On the big one you can have up to 8 if you squeeze it. So if you, when it comes out from the milling machine, it will look like this. So what we see here is this big metal piece is just the back support to keep it tight against the mask in the cross miller. And the sample is the black piece that we have here. The sample particular for today is electrode coated on paper. So the electrode side is facing upward. So your interesting side should always be facing against the titanium mask. That is upward in this picture. We just fixated with this tape piece. So after it comes out from the machine, we want to remove it from. I think this electrode that I have here is super fragile, so it's even detached from the tape by itself. Yeah, you see So the top one, yeah, the top edge here facing the camera is of course the cross section. So we don't want to touch that. So if you have several samples, one can just put the tapes like this, bum bum bum, in your notebook to keep them for later use. Remove that one also. So the fancy way of mounting these is to take a copper strip. It can be nice to make it, let's see, we can use the full width of it. Make it quite long. Better to have it a little bit longer than necessary. Like that. Always leave this on because it's so much easier for the next user. And here comes the fancy part. Now we want to put the tape facing the glue downwards like that. And make it press here so it really gets stuck. Then I fold it back. So now I have the glue facing upwards. I take my sample and then we want to cut it so we don't want such a long piece sticking up. We are only interested in the cross section. So the shorter you make it, the better it is. So if I can make it like 2 millimeters, that would be perfect. So that is just a waste. So let's see if I can get hold on this little tiny piece now. Like that. So then I put it here. Like that, so it gets stuck there in the corner. And then I fold this thing back. Like so. I press here with the tweezer so that cross section becomes really tight. Then I also squeeze here and then I fold it back. Like that, and now you're starting to see what's going on, right? Then we go for a second sample. They should be of the same height, all of them. Good if you don't flip them upside down. Alright, not the best version I have created, but it's good enough. Like that. Alright, starting to coming to the end here. Let's see if we can get this on, yeah, like that. So what we want to do now is take the tweezer and we flip these ones up, right? Now we want to flip them over, so we don't want them to be 90 degrees up in my case, because I have coated paper, so I'm going to sputter iridium on these now, on the back side, on the because the electrode itself is conducting. So that doesn't need any coating. It's the backside that's important. So then I make them like this, so they are at a 45-degree angle before I send them into the coater. So we can make a pause. All right, so here we can look on one that is already coated. So what I have done here, I took my marker pen and then I wrote the numbers from my sample so I can recognize them in the SM later on. And then they go into the sputter. I coat iridium on them, and then I flip them back up. So instead of this 45 degrees, I turn them back up to 90 degrees, but a little bit more. So they are like, if you look, they're a bit hard to see, but perhaps they are on 80 degrees. So the electrode side is facing upwards. And then you go and do the SM session. So now I'm going to show how to put the sample on here to make it ready for the cross-sectional machine tool, right? This one you remove. There is a round brass knob here. You just turn it with your finger here. And then this becomes loose, and you just take it up. And the sample will be clamped, you see here, between the mask and the back support. So this is the back support and this is the mask. So there are several back support pieces. And if you look, one of them has a machined edge here, or side. And if one looks on this direction, you can see that it is a little bit angled. That's the reason of the machining. So this one is the one that is preferred, and you're going to mount your sample on this chamfered side so that that piece goes against the mask. That means it will have a little bit of extra pressure against the top edge directly against the mask. So this is the preferred back piece to use. Alright, so we take both, we can bring both of this over to our lab bench. And this was your sample, right? So let's practice on your sample directly. See if it works. Can you remove these other ones? So we want to cut out a slice. The width can of course be the full width of this, but the cut will only be 4 millimeter. As you saw when I mounted it on the stub piece, it is nice to have some part that you can put on the tape on that is not your cross-section tool. So even if you cut this 4 millimeter wide, it can be nice if it's at least 6 millimeter wide to give you some handles. So we can take your whole section here, I guess.
Yeah.
Let's see if we can cut out of that, like that. Try to cut it here also. And the height of it should be like, if we put this next to here, we want it to sticking out a little bit on the top side, and we want the tape to be in the bottom part here. So that means around 10 millimeter or something like that can be a nice way. So let's try this. That is probably nice. So we take some tape. The width of the tape here, or length of the tape, should not be longer than the back piece. So it should be on the inside of the area here. So put the tape here on the bottom of your material, like that. And put the tape on the bottom part here. take the back size of my tweezer and press here so it comes together. So when we have reached this stage, we want to cut. I mean, we need to have the correct height above the mask, above the back support here. And this is a very important thing. I can draw a figure here in the book. If you come here and look closer. So let's say I take this thing with the mask and the back support that goes in here. I draw that from the cross-sectional view. So here is this titanium mask, right? Then our sample is mounted on this this back support, and the back support, you can just draw it like this. So and here there is a screw on top there. So I'm drawing it is in this direction now. So our sample is going to be clamped here between, right? So this is our sample. And this is the back piece. Right? The important thing here is that the titanium mask must be higher than the back support. Otherwise, when the beam comes over here and cuts everything off, it will cut off the back support piece also, and we don't want that. So the titanium mask must be higher than the back support, but the length, this height, cannot be like several millimeters as we have in our case, right? So we need to cut it down. But if we cut it down too much, then it will be, if this height is like less than 50 micron and things like that, then this titanium mask starts to coming below the back support, because when we adjust this in the machine later on, we're going to make the sample sticking up 50 microns above the titanium mask. So if I want 50 microns to be above the titanium mask, and this thing is less than 50 microns, that means, let's say it's only 30 microns sticking up. That means the titanium mask will in the end be 20 microns below the back piece, and I will cut through the back piece. So this is an important step. We need to cut this off with the scalpel knife, but we cannot cut it too much. So the smartest way of doing this is we place this facing down, like that. And the width of the edge of the knife is enough. So make sure that the screw that you have there is, the screw is spring-loaded. So make sure it is flat against the surface. We put this here, and we take the knife and we roll it with the knife directly facing flat against the back piece. Then you can see that there is one can see the copper foil here slightly sticking up, and that's exactly enough that we want. So this thing now we put here. You see the screw is going through that little lid slit, and we push this one up here, and before we make it completely tight, we look on the mask. Is the mask in fresh condition, or does it seem like it's been degraded? We can directly see that it's a little bit polished here. So it was used by the previous user on this position. So if you want this, you could probably run a little bit. It's not so wear down. You can run it a little bit longer if you like. But if you want a fresh surface, you can, of course, turn on this screw, and then you can choose where. So you can make a new fresh area. So let's move the mask over here, right? You can put it in that position. So now we see we have a completely fresh section of the mask. And if the whole side here is fully used, you unscrew the screw, flip it 90 degrees, put it back, and so on. So this little the whole thing here has a lot of screws on it. One says mask. So if I turn this, the mask goes down and up, right? Change it up and down. This one says Y. If I have it in the right way, it says Y. So that means it moves the sample up and down in the beam versus the beam, you can say, right? And then there is also a tiny screw there on the side that says X. So that's for adjusting the sample versus the beam in the X dimension. And then there is also a small screw they're calling R. And that is to, if the sample is like this, the edge of the sample might be angled. So then it allows you to rotate it in this direction. And to adjust all these positions, we do that in a microscope. So I have a microscope on the BIB tool here.
Yeah.
Yeah. So you see there's some knobs here. So this will only fit in one way. So when I put them here on the knobs, it just fits there. To turn on the microscope, you need to turn on the light. But before you can turn on the light, you need to turn on the machine. So you just turn on the whole machine. You can turn on light, get some light. And now we're going to adjust these screws, and for these screws we just use the fingers, but for these other ones we need the Allen keys. So there is these two different sizes of Allen keys, one for the small for rotation and one for the X. So I'm going to look here and adjust this, and I can perhaps take some picture later on and show when you move it. So the first thing you want to do, you focus the sample. So when you look here, you can most likely will just see the mask straight on. But you change the focus so you see the sample, and then you adjust so you get the right position of your sample. In our case, we just want to cut directly in the middle of the sample. We don't have any special demand. And I see it's a little bit wrong in the X direction. So I just turn here. So I get it completely centered in this way. And then I see it's also a little bit angled. So I need to rotate it a little bit. I do this. Like that. And then I can look on where the position is. I see the position is quite off, like 200 microns off in this direction. So here it's a little bit of a crucial step. So I haven't screwed this back piece, and you see there's still a gap here. I didn't put it directly flat. And the reason for not screwing this tight in the beginning is that if your surface is sensitive, if you squeeze it tight and you change the mask will scrape off your sensitive surface. You don't want that. So if it's very sensitive, you want to adjust this as good as possible before you make these things tight. So I do that, I change the height here, and then I look on the mask and see that it comes into a reasonable range. So as I said, we want the surface to sticking up 50 microns. So each tick in the hair cross in the microscope is 10 microns. So it's 5 ticks you're looking at. So I made a coarse adjustment of that now, and then I press this together, and then I can start to screw this thing tight here. And then I can look here and see how does it look like, and make some final adjustments. So if I look now, I can see that the sample is like, yeah, looks quite nice. The mask is 50 microns now from the edge of the surface. So then I can tighten this thing up so it comes tight. Everything looks nice. Yes. These two screws on the bottom here, those you should never touch. They are for calibration of the beam versus the whole thing here, so no users should play with this. So when I want to move this, it's very, now I shall detach this. So take around the bottom part here, because it's very easy you touch the screws by accident and then you change everything. I open this, screw it back, like that. Close the door, turn on the light for this other stereo microscope. There is a lid here, metallic cowl. So that lid is to protect the glass from being stained during this cutting or milling. So we need to remove that to see anything with a microscope. Then I look on my material and then I see, is my back piece lower than the mask, as we talked about before? And is it really clamped? Because if it's not really clamped, air gaps might be formed. And those air gaps between the mask and the surface create turbulence from the plasma, and that makes the coating look bad. So it's very important that it's flat. And I saw here it wasn't really tightened enough. So I looses this screw and then I try. It takes some time, some minutes, 2 minutes perhaps. Alright, so here is the case. So to check for this height differences with this stereo microscope, you need to have the microscope correctly set up so that you can get the proper vision with your eyesight. So this depends on your eyesight. If you have one eye is bad and the other one is good, you need to change different strengths. I mean, this is for people with glasses and things. So the first thing you do is you cover one of your eyes. Let's say you cover the left eye. And then you focus the sample with this knob. Right? And after this sample is in focus, you then do the reverse. So you look with your other eye. And then you change, if it's not in focus, the eye that you are looking with. So now you are looking with your left eye, so then you should change this scale here and to bring it into focus. So then you have adjusted for your eyesight, and after that it's important to also change the width. You can move these two apart depending on the width of your eyes to make proper stereoscopic visions, and then it should be easy for you to see what you're doing.
Yeah, you can really see the height difference now.
Yeah. So when the vacuum has finished, so they are reached a good vacuum level, these lights shows up to some numbers, everything lights up here. It was black in the beginning. So there's no so many settings you can choose here. The first thing you can choose is this level here. It says C1, C2, C3, 4, 5, 6. This is like a dishwasher program. So what this does is it changes when the beam, let's say the beam comes from this side, and let's say this is our sample, the beam will cut through this. These programs, they change a rotation, so it will continuously rotate back and forth like this. So the beam will cut in several directions like this. And the purpose of that is that if you have a heterogenic material with hard and soft pieces, you will get a very ugly cut if you just cut from one direction. So that's the reason why you do that. You can also change the angle so it rotates more or less, and also the speed of it, and that is these programs. And C3 is the one that most people use because that is like medium speed and medium angle. So it gives a wide cut. And you start with C3. If you're not happy with the result, then you can try something else. That's the rule of thumb. The other thing is how long time you want to run it. So you just program it here. So let's say you want to run it for 4 hours. set and it's programmed. 5 hours. So usually people run this machine during the night because it can take, depending on your material, it can take 12 hours. It can also be like 1 hour. And how fast it goes depends on your sample. If your sample is hard and solid and dense, if that's the case, then it will take longer time. But you can also change the strength of the beam or the accelerating voltage of the beam. So if you use a high voltage, it will be more aggressive and that will shorten the time, but it will also introduce heat into your sample. So if you're having a sensitive material like paper, you will start to burn off the paper over. So if it's a sensitive, fragile material, you might be forced running a very low accelerating voltage and running it for a long time. So that's the worst case. But if you have like metals, ceramics and things like that, you can run it at a high voltage and then the cutting time will be short. So let's turn on the beam then. So it says high voltage on off. I click here. Some numbers comes up here. Notice that this value is like 12, 13. That indicates that we don't have any plasma being ignited. So we just wait and see if it ignites by itself. It should do that. But the more dirty the machine becomes, because the plasma beam will suck up the material into the gun. So it acts like a vacuum cleaner and contaminates the gun after a while. And you can see on this counter, it's a 375 hours since last cleaning. So depending on the material you're cutting, around 100 hours is usually a good time to clean up the machine. But for paper electrodes, those are not so contaminated, so they you can run for a longer time. But anyway, if this doesn't start, one can try to increase the accelerating to full power, and then you can see if the beam ignites. Yeah, now you see it comes up into 200 range. So this current value you have here is directly proportional to the cutting rate. So the more dirty the gun becomes, the longer it will take. If it's a completely fresh and clean gun, you will have around 400 here. And if it goes below 200, then it's really dirty and needs to be cleaned up. So now we are at 240, so it's about time to clean up this now. So the only parameter for you to control is basically this accelerating voltage. So for paper, I run between 2 and 3. That is good for paper materials. You have just carbon on copper foil, so I think you can probably start perhaps with 4. And see how that turns out. These other meters, they usually are not of any use for the normal user, but what you can look on is this gas flow. It should be between 0.10 and 0.05 or something like that, so 0.8 is nice. And when you reach this stage, you just click start. And then you see this beam current goes blank, and if you look down here now, you can see it starts to oscillate back and forth. So that is this C3 program that's going. If you keep your camera still there, I can turn off the beam. Then you see that's the beam blocker. So if you make a pause, it looks like that. And then the current comes back up. So what we want to do now before we leave the machine, you can still film there. I close this lid cover now here, like that. Because it sprays debris up in the glass during the process. And when we have reached this state, we just wait. So I just turn off these lights. This went on and wait for 5 hours. And if you don't come back here, if you come back a little bit earlier, I mean, usually if you have a new sample, it is a trial and error. You need to find your settings for your material. So usually if it's a new sample, I usually come back every hour and take a look. I open the lid cover, turn on light, take a look. How is it progressing? Well, it's not finished, I need to run a little bit more. Okay, I close the lid, come back 1 hour and look. And if I find out that 5 hours has passed and I need to run it more, well, you can just pause it here, we set a new time and continue. So, and of course, if you think after 2 hours this looks fine, then you just stop it. So what's happening when you are done? So either you reach this stage, I'm happy with the result, then you can just stop it, and then you turn off the high voltage, and then you hold this air button to release the vacuum and fill it with air, and then you can pick out your sample. But if you come back after 5 hours, that's been going, like let's say you're running this overnight, so people usually sleep more than 5 hours. Then you come in the morning, then the machine will have a shut down itself after 5 hours. And what you need to do then is you need to turn on the power on the machine. But then you need to click twice on this button because it's already on now. So when the machine turns itself off, it do that internally, but the on button is still on. So you need to de-click the on button and then click it again. Then it starts up, and then you can evacuate or release the vacuum, fill it with air, pick out your sample. And then on our previous stage. So that's it.